The last method for string matching is the Rabin-Karp algorithm. At this point, you might wonder, we've seen a worst-case optimal algorithm. We've seen one that sometimes has good average behavior. We've seen a method that works on many typical texts. We've seen one that has the theoretical guarantees. What else could you hope for? And the only downside of those two methods is that they require extra space that's linear in the size of the pattern. There's situations where this is annoying if the pattern is very long, or if you're using this algorithm on a device with very little memory. And it's a very basic problem. It's just string matching. So maybe we can do something better than that. And indeed, we can. And this is where this last algorithm has its unique selling point. And the basic idea we use is hashing. I have not talked about hashing in this module at all. And we will not really talk about hashing apart from this part. So in case you've never seen this idea, a hash is just mapping some complex object to a small number. It's a fingerprint. That's why it's also written here. Although that term is a little dangerous, because for a fingerprint of a human, we usually think of fingerprints as being unique. All of our fingerprints are different enough so that an expert can distinguish them. The fingerprints here are not necessarily unique. The whole idea of hashing is to map a large universe of many, many different possible objects to a much smaller universe of fingerprints, so that all methods based on hashing have to live and work with collisions, that certain objects have the same fingerprint. But still, the term has been used, so I'll list it here in this sense, the computer science type of fingerprint. All right, how can hashing help in string matching? The core idea is we compute this fingerprint of the pattern, and then we just compare the fingerprint of the pattern to the fingerprint of a small portion of the text. And if they don't match, we know there's no match at this position. And if the hashes agree because of the collisions, we don't really know. It's likely to be a match, but we should still check to be sure. That's the Rabin-Karp algorithm in 2 minutes. The rest is fleshing out the details of how to do this efficiently. And I'll just briefly go over this. So let's see an example and just pretend that our texts have digits as alphabet symbols. That makes it a little more natural to talk about hashes where you just compute. So here we use a hash function that just takes the value and takes it modulo 97. So you take the integer division, x divided by 97, and whatever is the rest that remains, that's the result of this modulo operation. I'm sure you've seen this. So the idea here on the example is you take a certain guess where the pattern might occur. You compute the hash of this guess, which turns out to be 84, which is not the hash of the pattern, so we can move on. You take the next position, and there's again a different value, so you move on, and so on and so forth. Until here at that stage, you found the same hash, and it's in this case also an actual match. That's all there is to it. If you spell that out in pseudocode, it looks like this. You compute the hash of the pattern. The hash function will be of the same type that we've seen. It's essentially interpreting a string as a number over, well, taking the alphabet as digits of some base, and then you can interpret it as a number. And you could take modulo some number. That's some operation that defines your hash function. I won't go into details how to do that precisely. And then you compute the hash of a certain portion of the text, and you compare them. And only if they match, you actually go through character-wise and check if there's an actual match. All right? So the only problem with this code is if you compute a hash of a text of length m, you will essentially need time m because you have to work with all those digits. Now on a word RAM you might try to do some tricks of combining several characters into a single word, but let's not even try that here. It won't speed up the thing by more than a logarithmic factor. So essentially the computation of this hash is too slow to be interesting, because this would mean for every position in the text we spend theta m time. That's theta m times n. That's the same as the brute force method, so that's not interesting. But we're not done yet. It's not all hope is lost. We can find a specific type of hash function, a rolling hash, where we can move to the next position and update the hash in constant time. And the trick, intuitively, why this can work is if you move from one position to the next, you change one character at the beginning and you add one at the end, but there's a large portion in the middle that remains the same. So we just need a hash function that exploits this similarity between the two shifts. And well, one way to do this is essentially using these hash functions where you just compute modulo. So exactly the hash functions you've seen on the example on 2 slides ago. They happen to work, and to go through the details, I don't think I'll spend a lot of time on that. You can look at the example if you're interested. It's fairly straightforward. It doesn't have to do a lot with string matching. It's a general trick. Just see it as a black box for this class if you want. There are hash functions that work reasonably well where you can do this, go to the next position in constant time. And here's the details in code again. So where you do the computation like this. So this line is updating the hash. And if you ignore what's really computed there, you just look at the operation that we do. We do a minus, and we do a multiplication, and we add something, and then we do one modulo. All of those operations will take constant time if the numbers that are involved are not too big, and we can prove that they're not too big. OK, that was Rabin-Karp in fast forward. The worst case is still m times n, even though we could update the hash function in constant time. So the total time for computing all the hash values is essentially just theta of n, or theta of n plus m. Still, the worst case of the entire algorithm is theta n times m. Because if you're astronomically unlucky, you might pick a hash function that has many collisions. So even though there are no actual matches in your text, you would have to check them all. And a simpler version is if you have a very degenerate text where there's matches all over the place, the algorithm, OK, we report the first match. If you report all matches, you would have this bad case. If there's matches all over the place, you would report them and check them individually all. That's again something COMP can do this in linear time, even if you want to report all matches. Rabin-Karp in the version I've shown you wouldn't. It would have to compare all those matches character by character. But for inputs, if you're just interested in the first match, or if your text is not degenerate, and if you choose a good enough random hash function, then you can prove guarantees like the expected running time is n plus m. So you have to be very unlucky for this method not to work. So it's safe enough to rely on it. And it has other benefits in that this idea of hashing is very, very general. It doesn't only apply to this subword of the text. You can also do that if you're looking for patterns in an image, say. If you have a 2D text, All the other methods are not so easy to generalize, but Rabin-Karp would work. Well, and finally, talking about space, what we really store about the pattern while we're going, apart from the pattern, is just its hash value, its fingerprint, and that's a single number. So that's the only method that, apart from the pattern, which we have to store, only uses constant extra space. So in some applications, that's a definite selling point. I have another little question that I want you to answer on this. Again, just a little check of your understanding of this part. Right. Number 2 was clear. I guess I explicitly said that. It can happen that we find a collision, same hash, but no actual match. We never miss an occurrence if there is one, because no matter how stupid your hash function is, if you give it the same value, it's still a function. It will return the same value. So you won't miss any matches. But if you're very unlucky or, well, stupid enough in choosing your hash function, you might get many false positives. And the running time is a little tricky. This one is the correct running time, n times m, for the algorithm like it was on the slides. For the modification where you drop the check, you only need to compute the hash values. So it was a little sneaky way to ask for the time for just computing the hash. And that's actually n plus m. We compute the hash of the pattern first, and then roughly n times update it in constant time. I know I didn't go through the details of how to do that, so it was a bit unfair, but I think I mentioned it. All right, we can't do it in strictly n time because we have to start with the whole pattern. So some texts also present the Rabin-Karp algorithm as exactly that, only the hash value and not the check. And then it's an algorithm that's not always correct, but always fast. And often you can turn such a randomized algorithm into one that's always correct, but not always fast. That's the version that I presented. All right, that was all about the fundamental string matching methods. We'll talk a little more about strings and string matching from a different perspective. But here I prepared a little overview of the different techniques and their benefits. So this is nothing you wouldn't find on the other slides. It's just a summary. We will talk about suffix trees the week after next week, maybe. And these are the methods that we've seen in detail in this unit. As you can see, each and every single one of them has their right of existence. One are good in space, others are good in the worst case time, and yet others are good for many typical texts. So you will have to make your choice which one to use based on whatever's the application. Okay, that concludes the unit on string matching.